And now I think it's time to move on to Maria Diaz Trigo, search for interactions of X-ray binary outflows and their environments using ALMA. Maria, I'll give you a 3-minute warning.
Okay. Why I'm not seeing the... Do you see the screen? I'm just now. Okay, so hello everyone. And first of all, thanks to the organizers for giving me the opportunity to discuss here this topic of interactions of X-ray binaries and their environments with ALMA. To make it clear from the beginning, I'm not going to discuss jet ISM interactions. There was a whole discussion on Monday that you can watch on YouTube. Those of you that were not present, it was really educational and interesting. And I just want to remark regarding this discussion that somehow many different things, in my opinion, were discussed, even though, of course, they are all related to the jet passing through the ISM. But, you know, the picture that we have sometimes in AGN, like opening these cavities and so on, I mean, it's not, you know, the only picture that we are discussing here for X-ray binaries. We are seeing perhaps, you know, cavities being opened. We are seeing caps, you know, like the jet impacting on something, perhaps its own jet ejections before or shock regeneration or something. And we are seeing nebula being shaped by jets, but not produced by jets. So I just wanted to remark that and to remind you on the role of ALMA or the millimeter wavelengths in these studies. It was already mentioned as well on Monday, but you know, like the role of millimeter wavelengths is actually to explore the presence of molecules that are very sensitive to conditions of density, shocked environments, X-ray radiation, etc. So what the study of these molecules can help you is to characterize the sites of emission, okay, if you find any. And in this sense, pioneering work was already done more than 20 years ago, but indeed at that time, the telescopes in the millimeter wavelengths were not the best we can imagine. This has changed, of course, with the advent of ALMA, and now there's, you know, this work has been pursued by Alex Tetarenko and collaborators, and she has indeed found these kind of molecules in sites that had been previously identified as potential sites of jet ISM interaction. But again, as I said, I'm not going to discuss these interactions. I want to actually discuss the role of the wind in interacting with the environment. This is the reason why I am placed in this session. You have heard a lot about the accretion, these winds coming from X-ray binaries, and this is a field where we have learned a lot in the last 10 years, I would say. We know that winds are, you know, although X-ray winds are present probably or visible more in soft states, we know that winds, accretion, these winds are actually multi-phase. They are seen all the way from infrared to X-rays. They are present all along the outburst in different phases, perhaps. They are dense and they carry quite a lot of mass. I mean, regardless of the uncertainties that we are discussing or that Joy had discussed before. So they are also relatively wide angle if you compare them with jets. So the question is, you know, for AGN, there are similar winds, I mean, scaled to AGN scales, and they have actually, you know, been discussed for the past years intensively as providing feedback to the environment, and even it is disputed that they are the feedback agent. So the question is, what about X-ray binaries? Can, you know, these winds also provide feedback to the environment? Is this relevant at all or not? And to my knowledge, this hasn't actually been really discussed. So this is a topic that I'm interested in, perhaps because of my interest in wind, so I wanted to touch upon it. Now, one of the reasons that I find this is becoming interesting also in the late years is because in a way, when the feedback, you know, when you tell somebody, okay, what about the feedback from winds? Then they tell you, you know, they are slow compared to jets, so they are not going to provide enough energetic, kinetic energy to the environment. Now, I think there is a difference between, the agent itself being powerful and, the agent being capable or coupling to the environment, and therefore of depositing energy and momentum there. And in this sense, I find interesting the work that has been done recently on stellar winds and their effect on the ISM. The fact is that in the past, my understanding is that all the studies that were done on the relative feedback of radiation and winds concluded that the winds were completely irrelevant for feedback. But these studies were done for stellar winds that were moving in a cold ISM. Now, recent simulations have actually, they questioned that and said, we have these massive stars, they have a lot of radiation, at the course of time, these regions will become ionized, hot, etc. So the winds are not going to be propagating actually in cold ISM, but rather in hot ISM. So what about, the coupling there? And actually what they found is that the coupling, for the hot ISM, the coupling of the winds is so strong that they are higher, their feedback is much more relevant than the radiative feedback. So why do I think that this is relevant for X-ray binaries? I mean, as it has been discussed these days, the jets are being observed to travel undecelerated for the first days. This is being intensively studied now, but it was actually already studied many years ago. And this led to for example, Sebastian Heinz already in 2002 to propose that, X-ray binaries may be residing in underdense regions or regions surrounded by hot ISM. So you see the thing. I mean, if these X-ray binaries are really in cavities or in places, that where you have hot ISM, perhaps the coupling of the wind there is very important in order to transfer momentum to the environment. So this, as we heard for several speakers, I mean, the distances at which these jets start decelerating is actually sub-parsec. So it is very different to the kind of jet ISM interactions that I put on the first slide, where actually these are feedback at large spatial scales. Here we are really talking about relatively small spatial scales. And these are scales where I think winds may have actually a significant impact as well. So the questions that we wanted to answer with our project is, what is the feedback at these close environments of X-ray binaries? And actually, so can we observe a density change, where these jets start decelerating or at these scales? Can we observe anything that tell us, these cavities are everywhere? And if so, can we detect any impact of the wind in these cavities? And by the way, are the cavities, open by the jet or actually by the wind, which is wide angle and perhaps has much more power to inflate the bubble as it does, around the stellar winds? I mean, the clear example is the stellar winds. So this is from the discussion on Monday, actually, again, just to remind you that one of the open questions that was put there was, are these jets significantly impacting the ISM? So here you could ask yourself the same. I mean, regardless of whether there are winds and so on, are they really impacting the ISM, and how does this relate to jets? So again, the spatial scales that we targeted were from 0.5 parsec to 3 parsecs, depending on the X-ray binary distance, and we observed them at high resolution. And for lines, we actually, besides molecular lines that were typical of shocks, we actually look for hydrogen recombination lines. And the reason is that, these hydrogen recombination lines probably, exist in ionized environments, which we expect around close to these X-ray binaries. And, they don't have a bias as optical lines as of, stinted regions or not. We wanted to probe, a variety of binaries, and we didn't want to be biased, because of this. So
3 minutes, Maria.
Thank you. So here are the binaries that we observe. So surely you all know them. They are the ones that were always there. But the reason to choose these binaries, this set, was because they actually have a nice set of properties that that we want to explore, or we wanted to explore. So they comprise neutron star and black hole X-ray binaries. They comprise high mass X-ray binaries and low mass X-ray binaries, and they comprise systems that are at low and high inclinations. So where we can see actually the effect effect of, a very collimated jet, or rather a wind. And of course, like they all show jet emission, as you can see here, which is the continuum detections at 100 gigahertz with ALMA. And the ones that are high inclination, we have also seen powerful X-ray winds. So besides, again, these binaries and their close environment, we also targeted 2 regions where we know there are shocks, probably due to jets, one on the rim of this SIGX-1 nebula. I don't know if you see my mouse, but okay, the green circles here. And then on the caps along the jet of Circinus X1. And the reason was that we wanted to compare, again, any eventual line that we could detect to see whether it was different in these sites and on the other, close to the X-ray binary. So unfortunately, we didn't detect any line at all. I mean, all the detections that you saw, were on the continuum, except for one case that I will discuss next, and then we are not sure whether it is really related to the X-ray binary or not. But I will discuss it anyway in 1 minute, since we have some time. So this is the case of GX13+1. Here you see on the left the X-ray binary detected in continuum at 92 gigahertz. And this is the field of view of ALMA of this observation. And you see 3 lines, actually 4, that we detected in the surroundings. This is unrelated, surely unrelated. This is we think it's a SIO maser that is coincident with an object that could be a young stellar object or a evolved star. So interesting per se, but not for this project. But these other 2 lines are actually very different. I mean, they are spatially extended, so they showed up in scales up to 5 arc seconds in this plot. And they shared redshifts and, even type of lines in different locations, which made us think that, at least these 2 sites of emission might be related. We don't know if related to the X-ray binary, but at least related among them. So we identified them with SO and methanol at distances between 0.1 and 0.2 parsecs from the X-ray binary, if related to the X-ray binary. And the fact is that despite having, in our team, people, that were experts from star formation regions to, extragalactic AGN, like masers and so on, and evolved star, nobody could find a plausible explanation for this line. I mean, by cross-matching catalogs, etc., to other wavelengths. So what we did is also looking at the CO maps, 24 micron maps. The left one is done with JCMT and the right one with Spitzer. And what we saw was that the CO region is actually quite void, if you want, at this area. But interestingly, in the 24 micron map, the region closes up around the X-ray binary. And if you see here, the yellow diamonds are the signs of light emission, and they seem to be at the boundary somehow of this, cavity, whatever call you. So still, we don't know if this is, related or whether this is actually related to the X-ray binary at all, but we are trying to investigate that if ever we get that time with ALMA again, let's see. So to summarize, I mean, we searched for H-alpha recombination lines and SIO lines close to the X-ray binaries, but this search was largely unsuccessful, although the lines were also not detected at known shock sites related to jet emission. This could be, however, due to the limiting sensitivity of the line searches. So our searches had, the line sensitivity was, this was done for 5 years ago, the observations. And at that time, also the observations of Alex were not published. And the fact is that now when I compare, like the lines that she found with our sensitivities, it turns out that our sensitivities are just about, like the brightest lines that she finds. So perhaps this is a reason for not detecting anything. Perhaps they are just not there, and this was, completely wrong thoughts. So I'm happy to hear any idea that you may have, or, any reason for the non-detections. Thank you.
Okay, let's thank the speaker. Thanks, Maria. Do we have any questions from the floor? Let's start with that, as anyone can then pipe into Slack as well. Anyone from the floor, Jerome?
Nobody here. No question.
Okay, and let me add. So Maria, what are your plans? Oops, we have this question.
Yeah.
Jerome.
One question.
Okay, go for it.
Thanks, Andres Gurpide. I don't know if I understood correctly, but you mentioned that some bias with the optical lines as shock tracers. Could you comment on that? Or maybe I misunderstood that.
Well, I was thinking that if you want to explore regions that are very extended, you're going to be in trouble with the optical lines.
You can say it again, sorry.
If you are exploring regions that have a high extinction, if the binary happens to be in the line of sight of a high extinction line, then you are in trouble with the optical lines.
Okay, fair enough. Thank you.
All right, we have a quick question from Gregory Sivikov. So Greg, go ask away.
Hi, Maria. So thinking, is this something where we absolutely need ALMA sensitivity, or is there something where we can get away with longer observations with some of the other larger millimeter telescopes?
Well, I mean, it is a question of how efficient you are, right? These observations were half an hour each source. Okay, so it was an exploratory project. We thought it's very quickly done. What you definitely need is the spatial resolution. So you cannot go to single dish, which would save you, time or resources in big telescopes. Whether you can do it in other telescopes with similar resolution, you could on longer observations. I mean, these things are not supposed to be changing again as quickly as, hours or days. So yes, why not?
I guess I was thinking about doing single dish first to just detect the lines and then being able to follow them up with ALMA for the spatial resolution.
Well, the problem is that, again, this, if I think, for example, of Apex, which was for us the obvious option, the spatial resolution is 20 arc seconds. And here we're having resolutions of 0.1 arc seconds. And the regions that we have detected, perhaps they are completely unrelated to the X-ray binary, but they have a size of 5 arc seconds actually. So I think the single dish is not enough. I mean, there may be beam dilution. I mean, it is a question all of whether the regions are very extended or not. The maximum recoverable scales are an issue as well. So sure, if you think they are extended regions, then perhaps single dish would be enough. But I think we are probing two small regions that with single dish, I don't think we would be so efficient.
Thanks.
Okay, well, let's stop there and thank the speaker again. Just a brief announcement for